What if everything we thought we knew about the universe was just the tip of the cosmic iceberg? Picture this: ripples in the fabric of space-time, detected only a few years ago, confirming a prediction Einstein made over a century ago. These gravitational waves are like whispers from the cosmos, carrying secrets of colliding black holes and neutron stars. Yet for every mystery solved, a dozen more emerge, each more tantalizing than the last. From strange radio signals repeating in the depths of space to the invisible grip of dark matter shaping galaxies, the universe is far stranger than we ever imagined. This is where our journey begins with Cosmos Unveiled, a deep dive into the most perplexing and awe-inspiring questions that have haunted astronomers for centuries. Think about the night sky for a moment. To the naked eye, it's a tranquil sea of stars, but beneath that serene surface lies chaos, wonder, and phenomena that defy logic. Black holes, those cosmic vacuum cleaners, might not just be destroyers. What if they're portals to other realms? And dark matter, the ghostly substance that makes up most of the universe's mass, remains utterly invisible to us. How can something so pervasive be so elusive? These aren't just scientific puzzles, they're gateways to redefining reality itself. For generations, humanity has looked up and wondered, and now, with tools like the James Webb Space Telescope peering deeper into space than ever before, we're on the brink of revelations that could rewrite the textbooks. This video is your ticket to the frontier of cosmic discovery. We'll travel through time, from ancient astronomers who mapped the heavens with nothing but their eyes to modern scientists harnessing quantum physics to probe the universe's deepest secrets. Along the way, we'll confront theories that sound like science fiction: parallel universes, hidden dimensions, and the possibility that our entire cosmos is just one bubble in an infinite cosmic foam. By the end, you won't just understand these ideas, you'll feel the thrill of standing at the edge of the unknown, peering into the abyss and wondering what stares back. So buckle up, because the universe is stranger than fiction, and we're just getting started. Long before telescopes or satellites, humanity's fascination with the cosmos began with the naked eye and the rhythms of the night sky. Ancient civilizations turned stargazers into storytellers. The Babylonians etched the movements of Venus onto clay tablets over 3,000 years ago, weaving astronomy into astrology, where planets became gods and comets omens. The Greeks took it further, with thinkers like Aristarchus proposing a sun-centered universe centuries before Copernicus, only for the idea to be buried under the weight of Earth-centric tradition. Yet even then, meticulous observation thrived. Picture Hipparchus charting over 800 stars by hand, or Ptolemy mapping celestial motions with such precision his flawed Earth-centered model endured for 1,400 years. These weren't just skywatchers, they were detectives piecing together a puzzle with no edges, using only shadows, patience, and the turning of the seasons. Then came the Renaissance, a cosmic revolution. Galileo's trembling hands adjusting his crude telescope in 1609 didn't just reveal Jupiter's moons, they shattered the illusion of a perfect, unchanging heavens. Suddenly, the moon had mountains, the sun had spots, and the universe became a place of imperfections and motion. Copernicus' heliocentric theory, once a quiet mathematical footnote, now roared to life as celestial proof piled up. But here's the twist: for all their brilliance, these pioneers were still trapped by the limits of their tools. Tycho Brahe's legendary naked eye measurements of Mars paved the way for Kepler's laws of planetary motion, yet neither could imagine the swirling chaos of a black hole or the eerie glow of a quasar. That's the haunting beauty of cosmic curiosity. Every answer births new questions. the Babylonians tracking Venus would have been stunned to learn it wasn't a wandering god but a hellish world of crushing clouds. Galileo, who risked heresy to proclaim Earth moved around the sun, couldn't fathom that our sun itself orbits an invisible monster at the galaxy's heart. Today, we stand on their shoulders, wielding infrared telescopes and gravitational wave detectors to probe mysteries they'd consider pure myth. The Great Attractor, a gravitational anomaly dragging thousands of galaxies toward it, would have seemed like divine intervention to the ancients. Yet in a way, that thread connects us. The same wonder that led priests to align pyramids with stars now drives scientists to decode dark energy's whisper. So what changed? Not our hunger for answers, but the scale of our questions. Modern astronomy isn't just about charting paths, it's about peeling back layers of reality itself. The James Webb Space Telescope doesn't merely see farther, it sees back in time, capturing light from infant galaxies born in cosmic dawn. Radio telescopes eavesdrop on the universe's static, hunting for patterns in signals that might be natural or not. And just as Galileo's telescope upended dogma, today's tools are rewriting the rules. Maybe those ancient stargazers were onto something deeper, that the cosmos isn't just a clockwork mechanism, but a living, breathing enigma, always one revelation away from turning our understanding inside out. Here's a universe-shattering truth. Everything you can see, stars, planets, galaxies, makes up just 15% of all matter in existence. The rest, a ghostly substance called dark matter, invisible to every telescope ever built. It doesn't emit, reflect, or absorb light, yet its gravitational grip shapes the cosmos. The story of this cosmic phantom begins in the 1930s, when a sharp-tongued astronomer named Fritz Zwicky noticed something bizarre. Studying the Coma galaxy cluster, he saw galaxies whirling so fast they should have torn apart, unless some unseen mass was holding them together. He called it Dunkelmaterei, dark matter, and the scientific community shrugged. It took decades before Vera Rubin's meticulous observations of spinning galaxies confirmed Zwicky's hunch. Something invisible was pulling the strings. Today, dark matter is the universe's ultimate cold case. Theorists have proposed candidates WIMP, or weakly interacting massive particles, which barely interact with normal matter, or actions, hypothetical particles lighter than electrons. But catching them is like trying to grab smoke with your bare hands. Imagine standing in a pitch-black room, knowing a shadow lurks just beyond your fingertips. That's the frustration of experiments like the Large Hadron Collider, smashing particles at near-light speeds hoping to create dark matter in the debris, or detectors buried deep underground, waiting for a single, elusive collision. So far, silence. The stakes couldn't be higher. If dark matter isn't what we think, it might mean gravity itself works differently on cosmic scales. Some scientists, like those behind modified Newtonian dynamics, argue we've misread the universe's blueprint entirely. Picture rewriting the rules of a game while still playing it. That's the audacity of this idea. Yet most hold firm, dark matter is real, and its discovery would crack open a new chapter in physics. Think of it as the cosmic scaffolding, the hidden framework around which galaxies crystallized after the Big Bang. Without it, the universe as we know it wouldn't exist. And that's the irony. The very stuff that makes us possible remains just beyond our grasp. What if dark matter isn't one thing but many? Some models suggest entire dark sectors with their own particles and forces, a parallel universe tangling invisibly with ours. Others speculate primordial black holes, forged in the first chaotic seconds after the Big Bang, could be lurking in the dark. The truth is, every dead end in the lab only deepens the mystery. We're left peering into the abyss, armed with equations and ingenuity, chasing a shadow that may redefine reality itself. And that's the thrill. Dark matter isn't just a puzzle to solve. It's a reminder of how much we still don't know. In 1998, astronomers made a discovery so shocking it upended our understanding of the cosmos. Two teams studying distant supernova expected to see the universe's expansion slowing down, a natural consequence of gravity pulling everything together. Instead, they found the opposite. The universe wasn't just expanding, it was accelerating, as if some invisible force were pushing galaxies apart faster and faster. The culprit, a mysterious phenomenon dubbed dark energy. Unlike dark matter, which binds galaxies together with its gravity, dark energy seems to be doing the exact opposite, stretching spacetime itself. Einstein might have predicted it first, though even he didn't fully grasp the implications. His cosmological constant, a mathematical fudge factor he added to his equations to keep the universe static, was later called his greatest blunder when Hubble proved the cosmos was expanding. But now, dark energy has resurrected the idea. Could this constant, a sort of background energy woven into the fabric of space, be driving the acceleration? Or is something even stranger at work? Some theorists propose quintessence, a dynamic energy field that changes over time, unlike Einstein's static constant. Imagine the universe filled with an unseen fluid, its pressure fluctuating, sometimes pulling, sometimes pushing. The stakes are cosmic. If dark energy strengthens, it could lead to a big rip, a scenario where not just galaxies but atoms themselves are torn apart in a violent end to spacetime. On the other hand, if it weakens, gravity might regain control, collapsing the universe in a big crunch. Right now, we're blind detectives piecing together clues. The Euclid Space Telescope, set to map billions of galaxies, aims to trace dark energy's fingerprint by measuring how its push has shaped the universe over eons. What's surreal is this: dark energy makes up 68% of the universe's total energy, dark matter 27%, leaving the stars, planets, and us, everything we see and touch, a mere 5%. We're living in a cosmos dominated by shadows, where the fate of everything hinges on forces we can't see or feel. It's humbling. The same universe that once seemed orderly and predictable is now revealed as a dynamic, mysterious arena where invisible players hold all the cards. And just like that, the greatest story ever told, the life and death of the cosmos, has twists we're only beginning to read. Imagine a universe so vast, with hundreds of billions of galaxies, each containing billions of stars, many hosting planets in the perfect zone for life. The numbers alone suggest we should be swimming in extraterrestrial neighbors. So where is everybody? That's the Fermi Paradox, a question physicist Enrico Fermi blurted out during a casual lunch in 1950. His point was simple: if intelligent life is common, why haven't we seen a single trace of it? Decades later, with thousands of exoplanets discovered and telescopes scanning the skies, that silence feels louder than ever. One terrifying answer is the Great Filter, a hypothetical barrier that prevents life from reaching interstellar stages. Maybe it's behind us, some rare fluke like the jump from single cell to complex life, meaning we've already beaten impossible odds. Or worse, it's ahead of us, a catastrophe like nuclear war or runaway AI that wipes out civilizations before they can spread. The filter could explain why the cosmos seems empty. Most life gets snuffed out before it can say hello. But there are gentler possibilities. Advanced civilizations might be out there, just nothing like we expect. They could communicate in ways we can't detect, using neutrino beams or quantum entanglement instead of radio waves. Or perhaps they've moved beyond physical forms, existing as digital minds in Dyson spheres, harvesting starlight with no interest in primitive planets like ours. Even our own planet's history shows how easy it is to miss intelligence. Whale songs and dolphin clicks were dismissed as noise for centuries. Then there's the zoo hypothesis, the idea that aliens know we're here but are observing us like some cosmic nature preserve, waiting for humanity to reach a maturity worth engaging. It would explain why UFO sightings are fleeting and ambiguous, like shadows on a cave wall. And what about Amuamua, that bizarre interstellar object that zipped through our solar system in 2017? Its odd acceleration sparked debates. Was it a weirdly shaped rock, or, as some dared to whisper, an alien probe? So is the silence a warning or a challenge? Are we alone because life is vanishingly rare, or because the universe hides its secrets too well? Every new exoplanet discovered in the habitable zone, every anomalous signal from SETI antennas, pulls us deeper into the mystery. Maybe the answer isn't in the stars, but in the mirror, a test of whether humanity can survive long enough to solve the riddle ourselves. Black holes aren't just cosmic vacuum cleaners, they're shredders of reality itself. In 1974, Stephen Hawking dropped a bombshell. Black holes aren't entirely black, they leak. Through a bizarre quantum quirk, they emit faint radiation, slowly evaporating over eons. But here's the catch. According to Einstein's relativity, anything crossing a black hole's event horizon is gone forever, crushed into a singularity where space and time break down. Yet quantum mechanics insists information, the blueprint of every particle that ever fell in, can't simply vanish. It must be preserved, even if scrambled beyond recognition. This clash is the black hole information paradox, and it's one of the fiercest battles in modern physics. Imagine tossing a book into a fire. The pages burn, but the information, the words, the ideas lingers in the smoke and ash. In theory, you could reconstruct it, but a black hole, it's like burning the book in a furnace so extreme, even the ashes disappear. That's the problem. Quantum law says information is indestructible, so where does it go? Some theorists argue it's encoded in Hawking radiation, leaking out like a cosmic SOS signal. Others propose the holographic principle, that all the information inside a black hole is actually smeared across its surface, like a three-dimensional movie projected onto a two-dimensional screen. It's as if the universe is running a compression algorithm, cramming infinity into a finite space. Then there's the firewall paradox. Picture an astronaut falling into a black hole. Relativity says they'd glide smoothly past the event horizon, blissfully unaware until tidal forces shred them. But quantum mechanics suggests a horrifying alternative, a wall of ultra-hot particles just inside the horizon, incinerating anything on contact. Two flawless theories predicting utterly different fates. Who's right? The answer might lie in the first ever image of a black hole's shadow, captured in 2019, or in the ripples of gravitational waves detected by LIGO, revealing collisions where space itself rings like a bell. Each discovery chips away at the mystery. What's at stake isn't just academic. Solving this paradox could be the key to uniting Einstein's gravity with quantum mechanics, a theory of everything. It's like finding the missing piece of a jigsaw puzzle that's been scattered across dimensions. And the wildest part, black holes might not be the end of information, but a cosmic recycling plant, shredding reality only to spit it back out in some new, unrecognizable form. If that's true, the universe is far stranger and far more clever than we ever dreamed. Our galaxy isn't floating aimlessly through space, it's being pulled, along with thousands of others, toward something monstrous. Hidden behind the thick curtain of stars and dust in our own Milky Way lies a gravitational anomaly so powerful it bends the motion of entire galaxies. Astronomers call it the Great Attractor, and it's one of the most baffling mysteries in modern cosmology. The first clues emerged in the 1970s when scientists mapping cosmic motions noticed something odd. Galaxies within our local supercluster, including the Milky Way, were all streaming toward the same patch of sky near the constellation Centaurus. The speed was staggering, roughly 2 million kilometers per hour. But when they looked for the source, they hit a wall. The Milky Way's dense disk of stars and interstellar dust blocked the view. This region, dubbed the Zone of Avoidance, obscures nearly 20% of the visible universe from Earth's perspective. It's like trying to spot a lighthouse through a blizzard. You know it's there, but the storm swallows the light. So what's doing the pulling? One leading theory points to the Norma cluster, a massive gathering of galaxies about 250 million light-years away. Combined with surrounding superclusters, it might form a gravitational anchor dense enough to explain the motion. But here's the twist: even that might not be enough. Some calculations suggest the Great Attractor's pull requires up to 10,000 times the mass of the Milky Way. Could there be something even larger lurking behind the curtain? Exotic possibilities abound. Perhaps it's a concentration of dark matter so dense it warps space-time like a cosmic whirlpool. Or maybe it's the fingerprint of a primordial flaw in the universe's structure, a remnant from the Big Bang itself. The wildest theories whisper of a massive great wall of galaxies, a filament of the cosmic web so vast it defies imagination. But without clear observations, these ideas remain speculative. That's where technology becomes our lifeline. Telescopes like the James Webb, with its infrared eyes, can peer through the zone of avoidance by detecting heat signatures that visible light can't penetrate. Radio observatories like the upcoming Square Kilometre Array might map the hidden mass by tracing hydrogen gas swirling around unseen gravitational wells. Every new tool peels back another layer of the mystery, inching us closer to understanding the force that's tugging us toward the unknown. The Great Attractor isn't just a scientific curiosity, it's a humbling reminder of how much lies beyond our sight. For all our advances, the universe still holds cards close to its chest, daring us to look deeper. And as technology lifts the veil, we might find that the answer isn't just about what's pulling us, but what it reveals about the hidden architecture of the cosmos itself. In 2007, a team of astronomers sifting through old radio telescope data stumbled upon something extraordinary. A burst of radio waves so intense it blasted across the cosmos in just 5 milliseconds, packing more energy than the sun emits in 80 years. This was the first documented fast radio burst, or FRB, a phenomenon so fleeting and mysterious it seemed like the universe had winked at us. Since then, hundreds more have been detected, each a split-second flash of radio light from galaxies billions of light-years away. Some burst once and vanish, others repeat at irregular intervals like a cosmic heartbeat with no discernible rhythm. What could possibly unleash such titanic energy in the blink of an eye? The leading suspect is Magnetar's neutron stars with magnetic fields a trillion times stronger than Earth's. Picture a stellar corpse spinning furiously, its crust cracking under unimaginable strain. These starquakes might generate shock waves that ripple through space as FRBs. Then there's the cosmic comb theory. When a neutron star's jet plows through a cloud of plasma, it could create a series of rapid bursts like sparks from a grinding wheel. But the wildest hypothesis, that some FRBs are artificial beacons from advanced civilizations, or even power leaks from alien light sails tapping into galactic energy. The plot thickens with repeating FRBs. Unlike one-off bursts, these repeaters defy expectations by flaring up multiple times from the same location. In 2020, scientists traced one such repeater to a spiral galaxy remarkably similar to our own, ruling out extreme environments like supermassive black holes. This suggests FRBs might have multiple origins, some born in cataclysmic collisions, others from long-lived cosmic power plants. Enter CHIME, Canada's revolutionary radio telescope. Unlike traditional dishes, it scans the entire northern sky daily, catching FRBs in real time. Thanks to CHIME, we've catalogued hundreds of bursts, mapping their polarizations and frequencies for clues. One tantalizing pattern emerged. Some FRBs arrive with a telltale splash of lower frequencies slightly delayed, a sign they've traveled through turbulent intergalactic plasma. By studying these delays, astronomers can weigh the missing matter between galaxies, turning FRBs into cosmic measuring sticks. Could these bursts hold messages? While most scientists favor natural explanations, projects like Breakthrough analyze FRBs for artificial signatures, repeating numerical sequences or prime frequency spikes that might hint at intelligence. Even if they're just astrophysical, FRBs challenge our understanding of physics. Their energy defies known mechanisms, suggesting new particle interactions or even exotic objects like quark stars. Every burst is a cipher, a fragment of a language we're barely beginning to decode. And in that static, we might find not just answers, but new questions about the universe's boldest, brightest whispers. On August 15, 1977, a radio telescope at Ohio State University picked up a signal so extraordinary, it became legendary. For 72 seconds, a narrowband radio burst, 30 times louder than the background noise, blared from the direction of the constellation Sagittarius. When astronomer Jerry Amon reviewed the data printout days later, he circled the alphanumeric code representing the signal's intensity and scrawled, "Wow." In the margin, that single word gave the mystery its name. Decades later, the WOW signal remains astronomy's most tantalizing may have been, a whisper from the cosmos that vanished as suddenly as it appeared. What set it apart? The signal hit 1420 MHz, a frequency near the hydrogen line, a logical choice for interstellar communication since hydrogen is the universe's most abundant element. It wasn't random static, it was a focused, powerful transmission with the hallmarks of an engineered signal. Yet despite exhaustive searches using more sensitive equipment like the SETI Institute's Allen Telescope Array, it's never repeated. Not once. That absence fuels the debate. Was it a fleeting hello from another civilization, or just a cosmic prank? Natural explanations have crumbled under scrutiny. Some suggested comets, but none were in the area that night. Others proposed a passing satellite, but the signal's characteristics don't match known human-made sources. Pulsars, those spinning neutron stars, emit radio waves, but their rhythmic pulses look nothing like WOW's clean, sustained burst. Even atmospheric reflections or a glitch seem unlikely. The Big Ear telescope had redundant systems, and the signal appeared in only one of its two beams, ruling out terrestrial interference. The most electrifying possibility, a one-time beacon. Imagine an alien civilization sweeping the galaxy with a targeted radio burst, like a lighthouse beam grazing Earth for a moment before spinning away. Or perhaps it was a fragment of a longer message, most of it lost in the interstellar void. The truth might lie in between, a natural phenomenon we haven't discovered yet, something rarer than a pulsar or more exotic than a quasar. Here's what stings: we might never know. Without a repeat signal, WOW remains a cosmic Rorschach test, reflecting our hopes for contact or our fear of cosmic solitude. But it also raises a deeper question: how would humanity react if we did confirm an alien signal tomorrow? Would it unite us, as Carl Sagan dreamed, or fracture societies under the weight of existential shock? History offers clues. When Orson Welles' War of the Worlds broadcast fooled listeners in 1938, some panicked, others marveled. Today, with conspiracy theories spreading faster than facts, the reaction might be even messier. Yet WoW's legacy endures. It's a reminder that the universe is vast enough to hold mysteries we can't yet solve, and humbling enough to keep us listening. Every new telescope, every algorithm sifting through radio noise carries a sliver of that 1977 hope that somewhere, someone might be saying hello. And next time we'll be ready. The Big Bang Theory is one of science's greatest triumphs, explaining everything from the cosmic microwave background to the abundance of light elements like hydrogen and helium. But there's a glaring problem. Lithium, the universe's third lightest element, is missing. According to calculations, the intense heat of the early universe should have forged about 3 times more lithium than we actually observe. This isn't a small oversight, it's a gaping hole in our understanding of cosmic chemistry, forcing scientists to question whether they've missed something fundamental about the birth of the cosmos. The mystery starts with Big Bang nucleosynthesis, the process that fused the first atomic nuclei in the universe's fiery infancy. For the first 20 minutes after the Big Bang, temperatures and densities were so extreme that protons and neutrons collided, forming deuterium, helium, and trace amounts of lithium. The math seemed flawless. Equations predicted precise ratios matching what we see for hydrogen and helium. But lithium, observations of ancient stars, which preserve primordial material like cosmic time capsules, show only 1/3 of the expected amount. It's as if the universe misplaced an entire ingredient from its recipe. Where did it go? One possibility is that stars are the culprits. Over billions of years, lithium gets destroyed in stellar furnaces, fused into heavier elements. But even the oldest stars, which formed before lithium depletion could occur, show the same shortage. Another theory points to exotic physics. Perhaps unknown particles interacted with lithium in the early universe, breaking it down before stars could form. Experiments like Luna, which recreates primordial nuclear reactions underground, are testing whether lithium-producing reactions were miscalculated. So far, no luck. Then there's the radical idea. What if our models of the Big Bang are incomplete? Tiny variations in the universe's expansion rate or density could alter nucleosynthesis outcomes. Some researchers speculate that lithium's absence hints at multiple Big Bangs or even hidden dimensions influencing physics in ways we can't yet detect. It's a humbling thought that an element as simple as lithium might hold clues to rewriting cosmic history. The implications stretch beyond astronomy. Lithium is key to battery technology and fusion research. Understanding its cosmic scarcity could unlock new physics with real-world applications. For now, the missing lithium remains a quiet enigma, whispering that our picture of the universe's origins might still be a rough sketch. Every unsolved mystery is an invitation to look deeper, and this one challenges us to question not just where the lithium went, but whether we've been reading the universe's first chapter all wrong. The cosmic microwave background, the faint afterglow of the Big Bang, should be the universe's most democratic feature, a perfectly uniform canvas stretched across the sky. But in 2005, scientists poring over data from the WMAP satellite noticed something unsettling. The CMB wasn't as random as it should be. Instead, its hot and cold spots showed eerie alignments along a particular axis, as if the universe itself had a hidden equator. Dubbed the axis of evil by a physicist with a dark sense of humor, this anomaly threatens one of cosmology's sacred tenets, the cosmological principle. This principle states that, on large scales, the universe looks the same in every direction, no preferred location, no special axis. It's the foundation of everything from galaxy distribution to dark energy models. But the axis of evil suggests otherwise. Planck satellite data later confirmed the pattern, revealing that certain CMB fluctuations align with the plane of our solar system, a correlation so statistically improbable it's like rolling dice a million times and getting snake eyes every time. Could it be a fluke? Maybe, but the odds are worse than 1 in 10,000. Explanations range from the mundane to the mind-bending. Some argue it's an artifact of measurement, dust in our galaxy distorting the signal, or even the solar system's motion leaving a subtle imprint. Others propose more radical ideas. What if the universe isn't isotropic because it's shaped by something older? Pre-Big Bang structures, relics of a previous cosmic cycle, might have imprinted their geometry onto our newborn universe like a phantom fingerprint. Or perhaps dark energy isn't uniform but flows along unseen cosmic currents, tugging the CMB into alignment. The implications are staggering. If the universe has a preferred direction, it rewrites our understanding of its birth and fate. Inflation, the rapid expansion thought to have smoothed the early cosmos, might not have erased all traces of asymmetry. Instead, whispers of a deeper structure could linger, etched into the CMB like cosmic hieroglyphs. For now, the axis of evil remains an enigma, a crack in the facade of our isotropic universe. Whether it's a clue to a grander truth or just a cosmic mirage, one thing's certain: the cosmos still has secrets it isn't ready to give up. The Pioneer missions were supposed to be textbook examples of celestial mechanics twin probes, launched in the 1970s to study Jupiter and Saturn before sailing into the void. But by the 1980s, something odd emerged. Tracking their trajectories, NASA scientists noticed both spacecraft were slowing down slightly more than predicted, as if an invisible hand were tugging them backward. This tiny discrepancy, just 300 billionths of a meter per second squared, became the Pioneer anomaly, a nagging puzzle that defied explanation for nearly 3 decades. At first, the possibility seemed cosmic. Was it drag from interstellar dust, a flaw in our understanding of gravity? Some even whispered about dark matter's influence. But the answer, when it finally came, was surprisingly mundane: thermal radiation. The probe's radioactive power sources emitted heat unevenly, creating a faint but constant push in the opposite direction of their motion. Like a car idling with one window open, the escaping heat acted as a microscopic brake. The revelation was both satisfying and humbling, proof that even the smallest details can upend expectations. Yet the Pioneer anomaly's legacy lives on. It taught scientists to never dismiss tiny deviations, because sometimes they're clues to bigger truths. Take the flyby anomaly, where spacecraft like Galileo and Rosetta mysteriously gained speed during Earth gravity assists. These speed boosts, though slight, match no known physics. Some speculate hidden aspects of relativity or even exotic energy fields might be at play. Others argue it's another case of overlooked engineering, like unaccounted for radio signal delays. What makes these anomalies thrilling is their stubbornness. They refuse to fit neatly into our models, nudging us to question whether we've missed something fundamental. Every unexplained decimal point could be the thread that unravels or rewrites a law of physics. And that's the beauty of exploration. Whether the answer lies in quantum quirks or a loose thermal bolt, the universe keeps us honest, reminding us that curiosity isn't just about finding answers. It's about learning which questions we haven't even thought to ask yet. The Moon today is a silent, airless world with no global magnetic field, yet its rocks tell a different story. Samples brought back by Apollo astronauts contain tiny magnetic imprints, revealing something astonishing. Billions of years ago, our Moon may have had a dynamo core churning like Earth's. generating a magnetic field strong enough to shield its surface. This discovery rewrites lunar history because by all rights, the moon shouldn't have been able to pull it off. Magnetic fields require three ingredients: a molten, conductive core, rapid rotation, and vigorous convection. Earth ticks all boxes, but the moon, it's just 1% of Earth's mass too small, scientists assumed, to sustain such a powerhouse for long. So how did it happen? One leading theory points to a born hot scenario. Early in its history, the moon's core might have been superheated by the energy of its violent formation, the colossal impact that tore it from Earth's mantle. This heat could have fueled convection for a few 100 million years, driving a short-lived dynamo. But there's a catch. Some lunar rocks show magnetic signatures dating to just 3.5 billion years ago, long after the core should have cooled. That's where things get weird. Enter the impact-driven dynamo hypothesis. Imagine massive asteroids slamming into the moon, their energy stirring the core like a spoon in molten metal. Simulations show that such impacts could have temporarily reignited convection, creating sporadic bursts of magnetism. It's a cosmic defibrillator shocks reviving a dying core. Supporting this, lunar rocks from the Imbrium Basin formed by a giant impact carry particularly strong magnetic imprints, but not all scientists are convinced. Some argue these rocks might have been magnetized by plasma clouds generated during impacts, not a core dynamo at all. The stakes are higher than lunar trivia. If small bodies like the moon once had magnetic fields, it redefines what's possible for rocky worlds across the cosmos. Mars, too, shows evidence of a lost magnetic field, and Mercury, smaller than some moons, still has a weak one today. Could magnetic shielding be more common than we thought, expanding the zones where life might arise? Future missions like NASA's a Lunar Vertex rover aim to map ancient magnetic fields in real time, hunting for clues in the moon's dusty plains. What's clear is this: the moon's magnetic past is a puzzle with missing pieces. Whether powered by primordial heat, cosmic collisions, or some mechanism we haven't imagined, its fleeting magnetism whispers of a time when our closest neighbor was far more dynamic than the silent sentinel we see today. And buried in those lunar rocks might lie secrets not just about the moon, but about how all rocky worlds, including our own, come alive and then fade to quiet. 1,200 light-years away in the constellation Cygnus, a star named KC 8462852 behaves unlike any other. Nicknamed Tabby's star after astronomer Tabitha Boyajian, who first flagged its bizarre antics, this seemingly ordinary F-type star has a habit that defies explanation. It dims erratically, sometimes by as much as 22%, as if something massive and unseen is passing in front of it. These aren't the predictable dips caused by orbiting planets. They're chaotic, asymmetrical, and downright alien. The first clues came from Kepler, NASA's planet-hunting telescope, which monitored the star's brightness for years. Normally, Kepler's data reveals tidy, repeating patterns, the signature of planets transiting their host stars, but Tabby's star's light curves looked like a seismograph during an earthquake. One early theory proposed a swarm of comets, but the scale was all wrong. To block that much light, you'd need millions of comets, a scenario so unlikely it raised eyebrows. That's when the whispers began. Could this be evidence of alien megastructures like a Dyson swarm, a hypothetical array of energy-capturing panels built by an advanced civilization? Enter the citizen scientists. When professional astronomers couldn't crack the puzzle, Boyajian turned to the public through Kickstarter, crowdfunding further observations. Thousands of amateur astronomers joined the hunt, tracking the star's flickers with backyard telescopes. Their efforts paid off. In 2017, the star dimmed again, and this time telescopes worldwide caught it in action. The data revealed a critical clue. The dimming wasn't uniform. Some wavelengths of light were blocked more than others, pointing not to solid megastructures but to fine, uneven dust. Yet the mystery isn't solved. If dust is the culprit, why is it so patchy? Why does the star also show a century-long gradual dimming, as older photographic plates suggest? Some researchers propose a planet torn apart by gravitational forces, its debris creating a chaotic debris field. Others wonder if Tabby's star is consuming a nearby brown dwarf, the resulting turbulence kicking up vast clouds of obscuring material. What makes this enigma so compelling isn't just the what-if of aliens. It's the reminder that stars, even seemingly ordinary ones, can hide astonishing secrets. Tabby's star forces us to question our assumptions about how cosmic systems behave. Every anomalous flicker is a challenge to look closer, to imagine wildly, and to remember that sometimes the universe's most profound lessons come from its most stubborn outliers. And in that uncertainty lies the thrill, because the next time this star dims, we might finally catch it in the act of revealing its truth. Saturn's North Pole holds one of the solar system's most mesmerizing geometric oddities, a perfect six-sided hexagon, wider than Earth itself, churning in the planet's atmosphere like a colossal cosmic tattoo. First spotted by Voyager in the 1980s and later studied in stunning detail by Cassini, this structure defies everything we know about fluid dynamics. Storms on planets, even gas giants, tend to be chaotic swirls or ovals. Think of Jupiter's Great Red Spot. But Saturn's hexagon, it's razor-sharp, with sides stretching nearly 14,000 kilometers, and it's been spinning in place for decades, possibly centuries. How does nature craft something so precise in a turbulent, hydrogen-rich atmosphere? Scientists have turned to lab experiments and supercomputer simulations to crack the puzzle. One leading theory suggests the hexagon is a standing wave, a pattern created by differences in wind speeds at various latitudes. Imagine stirring a cup of tea. The liquid forms vortices, but under specific conditions, those swirls can lock into geometric shapes. On Saturn, jet streams racing at over 300 kilometers per hour might interact with the planet's rotation to stabilize this six-sided freak of nature. Lab experiments using spinning fluids have recreated similar polygons, but none as persistent or massive as Saturn's. There's also the wild card of depth. The hexagon might be rooted far below the visible cloud tops, where denser layers of atmosphere amplify and shape the pattern like an invisible mold. Now contrast this with Jupiter's polar storms. While Saturn boasts a single geometric wonder, Jupiter's poles are crowded with cyclones, 8 tightly packed around a central one at the North Pole, 5 at the south arranged like petals on a nightmarish flower. These storms are deep, turbulent, and constantly jostling, yet they've maintained their formations for years. Why the difference? It might come down to internal heat. Jupiter radiates more energy than it receives from the Sun, fueling violent convection that births multiple storms. Saturn, though colder, has a more stable atmospheric structure, possibly allowing orderly waves like the hexagon to dominate. The hexagon's endurance raises deeper questions. Is it a temporary feature, or has it been there since Saturn's youth? Could similar structures exist on exoplanets, hidden in distant star systems? And what about its south pole? Why no matching hexagon there? Some speculate asymmetries in Saturn's magnetic field or internal heat distribution play a role, but no one knows for sure. What's clear is this: the hexagon isn't just a curiosity, it's a classroom. By studying it, we're learning how planetary atmospheres self-organize, how chaos can give rise to order, and how much we still don't understand about the giants in our cosmic backyard. Every time we look, Saturn reminds us that even the familiar can harbor the extraordinary, if only we know where to look. In October 2017, astronomers spotted something unprecedented, a visitor from another star system, tumbling past the Sun at blistering speeds. Named Oumuamua, Hawaiian for scout, this interstellar interloper defied every expectation. Most comets and asteroids follow predictable orbits, but Oumuamua's trajectory was hyperbolic, meaning it wasn't bound to any star. Even stranger was its shape. Estimates suggested an elongated, cigar-like structure, 10 times longer than it was wide, unlike any natural object we've seen in our solar system. But the real shock came when telescopes detected something impossible. Oumuamua was accelerating, as if pushed by an unseen force. Normally, comets speed up due to outgassing, sunlight vaporizing their ice, creating a visible coma and tail. Yet Oumuamua showed no such signs, no dust, no gas, no glowing trail. So what was propelling it? One theory points to hydrogen icebergs, chunks of frozen hydrogen that sublimate in sunlight, leaving no visible trace. In the cold depths of interstellar space, such ice could form, but critics argue hydrogen ice would evaporate too quickly near a star. Another idea involves nitrogen ice, similar to Pluto's surface, but again, the numbers don't quite align. Then there's the more provocative explanation. Could Oumuamua have been artificial? Harvard astronomer Avi Loeb famously suggested it might be a light sail, a thin, reflective structure pushed by starlight, perhaps even debris from an alien civilization. The idea isn't entirely far-fetched. Humanity's own light sail project proves the technology works, but without definitive proof, the scientific community remains divided. The truth is, Oumuamua left as mysteriously as it arrived, slipping beyond our telescope's reach before we could gather enough data. This cosmic missed opportunity underscores a glaring gap in our capabilities. Oumuamua was only spotted as it was leaving. What if we'd caught it earlier? Future projects like the Vera Rubin Observatory aim to scan the skies more thoroughly, ensuring we don't miss the next interstellar visitor. Because whether it's a hydrogen iceberg, a rogue fragment from a distant planet, or something even stranger, these travelers carry secrets from realms we've yet to explore. And next time we'll be ready, not just to watch, but to chase, to study, and perhaps to finally understand. The cosmic microwave background is often called the universe's baby picture, a near-perfect snapshot of its infancy, glowing faintly in every direction. But in this primordial light, there's a blemish that shouldn't exist. A vast, inexplicably cold patch spanning nearly 200 million light-years, lurking in the constellation Eridanus. Dubbed the CMB cold spot, this region is up to 70 microkelvin colder than its surroundings, a discrepancy so stark it defies standard cosmic models. At first glance, it might seem trivial, a statistical fluke in the CMB's gentle fluctuations, but the odds of such a cold spot forming randomly, less than 2%. This isn't just a cosmic typo, it's a screaming anomaly. So what could carve such a frigid gash in the fabric of the universe? One leading theory points to a supervoid, an enormous, sparsely populated region of space where galaxies are eerily scarce. In these cosmic deserts, photons from the CMB lose energy as they traverse the void's weakened gravitational pull, a process called the integrated Sachs-Wolf effect. It's like rolling a ball uphill. By the time it reaches you, it's slower, cooler. But here's the catch. The cold spot's size and temperature drop don't quite match known supervoids. Surveys have found underdensities nearby, but nothing vast enough to explain the chilling effect. It's as if we've found a footprint, but the giant who left it is nowhere in sight. That's where things get surreal. Some theorists propose the cold spot isn't a void at all, but a bruise from a collision with another universe. In the multiverse scenario, our cosmos might be one bubble in an infinite froth of universes, each with its own physical laws. If a neighboring bubble brushed against ours in the distant past, the energy exchanged at the boundary could have left a mark, an imprint cooler than its surroundings. It's a radical idea, but not without precedent. The same quantum fluctuations that seeded galaxies might also have spawned other universes, their edges pressing invisibly against our own. Critics argue such theories leap too far beyond observable evidence, yet the cold spot's persistence challenges them to offer better answers. Could it be an artifact of incomplete data or a quirk of how we measure the CMB? Blank satellite observations have only deepened the mystery, confirming the anomaly's existence while leaving its origin wide open. What's undeniable is this: anomalies like the cold spot aren't just wrinkles in our maps, they're stress tests for cosmology itself. Every time we tweak our models to explain them, we're forced to ask, are we missing a piece of the puzzle, or is the puzzle far bigger than we ever imagined? Perhaps the most humbling lesson lies in the silence. The cold spot doesn't announce its secrets. It simply exists, a quiet enigma drifting in the afterglow of creation. Whether it's a void, a multiverse collision, or something beyond our current physics, one thing's clear: the universe is still teaching us how much we have left to learn. And in that vast, uncharted territory between theory and observation, discoveries await that could rewrite not just our maps, but our understanding of reality itself. Galaxies are supposed to follow rules: spirals with their graceful arms, ellipticals like cosmic footballs, all bound together by the invisible glue of dark matter. Then there's NGC 1052DF2, a galaxy that didn't get the memo. Discovered in 2018, this ghostly smudge of stars in the constellation Cetus does the unthinkable. It appears to have almost no dark matter at all. At first, astronomers assumed it was a mistake. Dark matter is the scaffolding of the universe, the hidden hand that shapes galaxies. Without it, stars should fly apart like beads from a snapped necklace. Yet DF2's stars move sluggishly, their speed so low that the galaxy's visible mass alone can account for its gravity. It's as if someone removed the foundation of a skyscraper, only for the building to stand perfectly still. How could such a cosmic rebel exist? One theory suggests a violent past. Perhaps DF2 was born from gas stripped away during a collision between larger galaxies, leaving its star rich but dark matter poor. Another idea posits that tidal forces from a neighboring galaxy, NGC 1052, siphoned away its dark matter like a thief in the night. But here's the twist: follow-up studies found a second dark matter deficient galaxy, DF4, nearby. Two outliers might be a coincidence, but it starts to look like a pattern. The implications are seismic. If these galaxies formed without dark matter, it challenges the very bedrock of modern cosmology. The prevailing model, called lambda cold dark matter, relies on dark matter's gravitational pull to explain how galaxies clump together. Take that away, and suddenly we're left scrambling for alternatives. Could there be a flaw in our theories? Some researchers propose modifications to gravity itself, like modified Newtonian dynamics, which tweaks the rules to explain galaxy rotations without invoking dark matter. Yet MUND has its own problems, struggling to account for phenomena like the bullet cluster, where visible matter and gravitational effects are clearly separated. Then there's the tantalizing possibility that DF2 isn't an outlier but a signpost. Maybe dark matter isn't the uniform, all-pervading substance we assumed. Could it clump unevenly, leaving voids where galaxies like DF2 can form? Or perhaps dark matter interacts with itself in ways we haven't discovered, sometimes pooling, sometimes scattering. The discovery of more dark matter-free galaxies could tip the scales, forcing us to rewrite the cosmic playbook. For now, DF2 remains a cosmic provocateur, daring us to question what we think we know. Every time we find a rule in the universe, nature seems to whisper, there's always an exception, and in those exceptions, hidden in the faint glow of an oddball galaxy, might lie the next great leap in understanding the cosmos. Beyond Neptune's orbit, in the frozen fringes of our solar system, something strange is happening. The Kuiper belt, home to icy worlds like Pluto, should be a realm of predictable orbits shaped by the known planets. Yet a handful of its most distant objects move as if tugged by an unseen hand. Their paths cluster together, tilted at angles that defy standard models, and their elongated orbits point eerily in the same direction. This cosmic choreography has led scientists to a startling hypothesis: a hidden planet, perhaps 10 times Earth's mass, lurking in the darkness. They call it Planet 9. The evidence isn't just circumstantial, it's written in the math. In 2016, Caltech astronomers Konstantin Batygin and Mike Brown noticed that 6 distant Kuiper belt objects shared orbital peculiarities. The odds of this alignment happening by chance, a mere 0.0002%. Their simulations showed a massive, undiscovered world could shepherd these objects into their unusual paths, much like Neptune's gravity once explained irregularities in Uranus's orbit. The hypothetical Planet 9 would follow a stretched, elliptical path, taking between 10,000 and 20,000 years to complete a single trip around the Sun, so distant it would reflect almost no sunlight, rendering it nearly invisible to telescopes. But the hunt is on. Observatories like Subaru in Hawaii scan the skies for faint glimmers, while projects like the Vera Rubin Observatory aim to map the outer solar system in unprecedented detail. Every unaccounted-for motion in the Kuiper belt is a potential clue, yet skeptics argue alternative explanations might fit the data. Could a passing star have yanked these objects into odd orbits long ago? Or might the collective gravity of smaller, unseen Kuiper belt objects produce the same effect? Some even suggest modifications to gravity itself, like modified Newtonian dynamics, though this struggles to explain the clustering as neatly as Planet 9 does. The implications go beyond one missing world. If Planet 9 exists, it challenges our solar system's origin story. How did a planet that massive end up so far out? Was it flung there during the chaos of the early solar system? Or could it be a captured rogue planet, born around another star? Each scenario reshapes our understanding of how planetary systems form and evolve. And if it's not there, the very anomalies prompting the search might hint at gaps in our grasp of gravity or cosmic history. For now, the Kuiper belt's wayward objects keep their secrets. Whether the culprit is a hidden giant, a stellar interloper, or something even stranger, their twisted paths remind us that the solar system's story isn't fully written. Every odd orbit is a question, and the answer might rewrite the map of our celestial neighborhood. In 2019, astronomers scanning the sky with Australia's ASCAP radio telescope stumbled upon something that defied all expectations: enormous, perfectly circular rings of radio emission, each spanning hundreds of thousands of light years. These odd radio circles, or ORC, appeared like cosmic bullseyes, invisible to optical telescopes but blazing in radio wavelengths. The discovery sent shockwaves through the astronomy community, not just because of their sheer size, some could engulf entire galaxies, but because no one could explain what they were. Theories erupted like supernova. Were these the aftermath of colossal intergalactic explosions, the echoes of black hole mergers, or something entirely new, a phenomenon we'd never even imagined? One leading hypothesis suggests ORCs are shockwaves from titanic galactic collisions. When galaxies merge, their supermassive black holes can fling stars and gas outward at near light speeds, creating ripples in the intergalactic medium. These ripples might then glow in radio waves as they interact with magnetic fields, like the wake of a ship lighting up phosphorescent algae. But there's a problem: ORCs are too symmetrical, too isolated. Most merger remnants are messy, asymmetrical affairs, not these pristine rings. And why don't we see any visible traces of the galaxies that supposedly collided? It's like finding a perfect smoke ring in the sky with no sign of the pipe that blew it. Then there's the neutron star angle. Some propose ORCs are the remnants of hyper-energetic bursts from magnetized neutron stars with magnetic fields so strong they could strip atoms apart. If one of these monsters released a gamma-ray burst in just the right way, it might carve a spherical shock wave into the surrounding gas, visible only in radio. But again, the scale is baffling. ORCs are hundreds of times larger than any known neutron star remnant, and their uniformity suggests a single, cataclysmic event rather than an ongoing process. The wildest theory: ORCs might be the throats of wormholes, their intense gravitational lensing bending radio waves into circular patterns. Or perhaps they're the signatures of dark matter annihilations, where invisible particles collide and release bursts of energy. These ideas sound like science fiction, but that's the point. ORCs don't fit neatly into any existing box. They're forcing scientists to rethink what's possible. New telescopes like the Square Kilometre Array are now hunting for more ORCs, mapping their structure in unprecedented detail. Each new detection could crack the case wide open. Are these cosmic accidents or the first glimpses of a hidden layer of the universe? One thing's certain: in a cosmos full of mysteries, ORCs might just be the most perplexing yet. And the answers, when they come, could rewrite the rules of astrophysics. Deep in the constellation Monoceros, about 2,300 light-years from Earth, a cosmic masterpiece defies the usual chaos of dying stars. The Red Rectangle Nebula isn't just another cloud of gas. It's a near-perfect geometric sculpture, its glowing latticework of lines and corners so precise it looks engineered. Most planetary nebulae, the final exhalations of sun-like stars, resemble tangled fireworks or delicate soap bubbles. But this one, it's as if nature grabbed a ruler and protractor, crafting a structure more fitting for a cathedral's stained glass than the depths of space. The secret to this symmetry lies in a dance of destruction. At the nebula's heart sits not one, but two aging stars locked in a tight orbit. As the primary star shed its outer layers in its death throes, the gravitational pull of its companion sculpted the escaping gas into twin cones. Viewed from Earth, these cones align edge-on, creating the illusion of a rectangle. But it's the finer details that dazzle: delicate rungs of dust and gas stretching between the walls like ladder steps, formed by shock waves as the star's stellar winds collide. This isn't random chaos, it's physics as an artist turning turbulence into breathtaking order. What's truly remarkable is how fleeting this perfection is. The red rectangle's geometry won't last. In a few tens of thousands of years, a blink in cosmic time, the nebula will dissipate, its once crisp edges blurring into the interstellar medium. That makes it a rare snapshot of balance in a universe that usually favors entropy. It's a reminder that even in death, stars can create something staggeringly beautiful, provided the right partners and conditions align. This nebula also challenges our assumptions about complexity. Often, the universe's most striking features arise from simple rules played out over vast scales. The red rectangle's precision emerges from basic orbital mechanics and fluid dynamics, no exotic physics required. Yet witnessing such perfection in the wild forces us to wonder how many other celestial wonders hide in plain sight, their elegance masked by distance or dust. Every time we train our telescopes on these cosmic oddities, we're not just solving puzzles, we're learning to see the universe anew. Imagine a planet where the ground beneath your feet isn't rock or ice, but solid diamond. A world so dense and glittering it could make Earth's crown jewels look like costume jewelry. That's not science fiction, it's PSR J171938B, a celestial oddity orbiting a pulsar 1,200 light-years away in the constellation Serpens. Discovered in 2011, this planet is the stuff of cosmic legend, forged in the aftermath of a stellar explosion so violent it left behind a spinning corpse of pure neutron star and a world made of crystallized carbon. Pulsar planets are already cosmic rarities, only a handful have ever been confirmed. The reason? The supernova explosions that create pulsars are so cataclysmic, they typically vaporize any nearby worlds. But PSR J171938B somehow survived, or more likely, formed from the ashes. Here's how. The pulsar it orbits is a millisecond pulsar, spinning hundreds of times per second, its beams of radiation slicing through space like a lighthouse on overdrive. This pulsar wasn't always so fast. It gained speed by cannibalizing its companion star, stripping away layers until only the star's carbon-rich core remained. Under unimaginable pressure, that core crystallized into diamond, becoming the planet we see today, a world roughly 5 times Earth's mass, compressed into a sphere smaller than Jupiter. The conditions there are beyond extreme. The diamond planet orbits so close to its pulsar that a year lasts just 2 hours. Bathed in intense radiation and gravitational tides, its surface, if you could call it that, would be a jagged, luminous plane, shimmering under the pulsar's relentless glare. There's no atmosphere, no liquid, just an eternal, crushing stillness where carbon atoms are locked in perfect crystalline lattices. What's most thrilling isn't just this planet's existence, but what it implies. If diamond worlds can form around pulsars, what other exotic varieties lurk in the cosmos? Could there be planets made of sapphire, their blue hues forged in the hearts of dying stars? Or worlds of pure iron, sculpted by supernova into metallic spheres? The discovery of PSR J171938B cracks open a door to possibilities we're only beginning to explore. Every time we find a world like this, it's a reminder that the universe's creativity outshines our wildest dreams. From diamond planets to lava worlds, the cosmos doesn't just build planets, it crafts masterpieces. And somewhere out there, in the silent dark, another impossible world is waiting to be found. The universe isn't just a scattering of galaxies, it's a vast cosmic web, with filaments of matter stretching across unimaginable distances, connecting dense clusters like pearls on a string. But in the constellation Boötes, there's a hole in the fabric, a yawning, spherical void so empty it defies comprehension. Stretching over 300 million light-years, the Boötes void contains just 60 galaxies where there should be thousands. If the Milky Way sat at its center, we wouldn't have known other galaxies existed until the 1960s. This isn't merely a quiet neighborhood, it's a cosmic desert so barren it challenges our understanding of how the universe arranges itself. What could carve such a void? One possibility is as simple as it is unsettling: random chance. In an infinite universe, even the most improbable configurations must exist somewhere. Like flipping a coin a billion times and getting tails every so often, the Boötes void might just be a statistical anomaly, a blank spot in the cosmic quilt. But the numbers strain credulity. The odds of a void this large forming naturally are less than 1 in a million. That's led scientists to hunt for more exotic explanations. Could it be the footprint of an ancient collision between our universe and another bubble in the multiverse? Or perhaps dark energy, that mysterious force accelerating cosmic expansion, worked overtime here, pushing matter away like a cosmic plow? Then there's the eerie alignment. The Boötes void sits perpendicular to the plane of our solar system, a geometry so precise it feels intentional. Some theorists speculate that supermassive black holes in the early universe might have merged, releasing titanic gravitational waves that cleared matter from vast regions like a broom sweeping dust. Others suggest the void is evidence of a cosmic defect, a tear in spacetime's fabric left over from the Big Bang. But the most haunting idea, that we're seeing the shadow of something even larger, a structure so vast its gravity has drawn galaxies away like a cosmic tide, leaving only echoes of emptiness. The Boötes void isn't just a curiosity, it's a stress test for cosmology. If voids this size can't form under current models, does that mean our maps of the universe are incomplete? Or does it hint at forces we haven't yet discovered, lurking in the darkness between the stars? Every time we point our telescopes at this emptiness, we're confronted with the same humbling truth. The universe is far stranger and far more inventive than we ever imagined. And in that vast, silent void, there might be answers waiting, if only we learn how to listen. When the James Webb Space Telescope began peering into the cosmic dawn, scientists expected to see the universe's first galaxies in their infancy, clumsy, fragile collections of young stars still finding their footing in the early cosmos. Instead, JWST delivered a shock, galaxies that looked far too grown up for their age. These ancient systems, spotted just 300 million years after the Big Bang, weren't the expected cosmic toddlers. They were fully formed, massive, and brimming with complex structures, spiral arms, disks, and even bars, features that, according to current models, shouldn't have had time to develop. It's like finding a fully furnished skyscraper in the middle of a construction zone, and it's forcing astronomers to rethink everything they thought they knew about how galaxies are born. The problem lies in the timeline. Conventional wisdom says galaxies start small, slowly accumulating gas and dust over billions of years through mergers and steady star formation. But JWST ultra-deep images reveal galaxies 10 times more massive than predicted, some hosting as many stars as the Milky Way despite existing when the universe was less than 2% of its current age. These galaxies shouldn't just be rare, they should be impossible under standard cosmology. So what's going on? One radical idea suggests star formation in the early universe operated at breakneck efficiency, converting nearly all available gas into stars almost instantly. Another theory posits that dark matter, the invisible scaffold of the cosmos, clumped together far faster than simulations predict, creating gravitational wells where galaxies could assemble at warp speed. Then there's the wild card. Could these galaxies be older than we think? If the Big Bang wasn't the absolute beginning but followed an earlier phase of cosmic expansion, a theory called cosmic inflation on steroids, it might buy the extra time needed for these behemoths to form. Alternatively, perhaps our understanding of stellar physics is incomplete. Maybe the first stars burned hotter, died younger, and seeded their galaxies with heavy elements much faster than today's stars, accelerating galactic evolution in ways we haven't accounted for. The implications ripple far beyond a few overachieving galaxies. If early structure formation was this rapid, it could mean the universe's formative years were far more dynamic and chaotic than we imagined. Supermassive black holes, which typically take billions of years to grow, are also appearing suspiciously early in JWST data, suggesting a deeper link between galaxy and black hole formation than current models allow. Every new observation chips away at the comfortable certainties of cosmology, leaving us with a universe that's stranger, more inventive, and far less predictable than we ever dared to dream. What's thrilling isn't just the mystery, but the opportunity. JWST discoveries aren't breaking cosmology, they're stretching it, revealing gaps where new physics might hide. Whether the solution lies in tweaking dark matter's behavior, reimagining the early universe's expansion, or rewriting the rules of star formation, one thing's clear: the cosmic dawn was no gentle sunrise. It was a fireworks display, and we're only just beginning to see the sparks. Picture the universe not as a random scatter of stars, but as an intricate, glowing spiderweb, threads of galaxies stretching billions of light years, intersecting at dense clusters like knots in a net. This is the cosmic web, the hidden architecture of everything, and it holds more secrets than we ever imagined. The eerie part: most of this structure is invisible. What we see, the glittering galaxies and glowing gas, is just the icing on the cosmic cake. The real skeleton, the scaffolding that shapes the universe, is woven from dark matter, that mysterious substance that neither emits nor reflects light yet dictates where galaxies form and how they move. Scientists first glimpsed this hidden framework by studying the peculiar motions of galaxies. Why do galaxies drift like leaves on a river, even when there's no visible current? The answer lies in the gravitational tug of dark matter filaments, vast rivers of unseen mass flowing between galaxy clusters. These filaments can stretch for hundreds of millions of light years, funneling gas and galaxies along their lengths like cosmic highways. Mapping them isn't easy, but tools like gravitational lensing, where light bends around massive objects, reveal their ghostly outlines. It's like tracing the shape of a shadow in the dark, feeling the presence of something colossal just beyond sight. Now here's the twist: the cosmic web might hold the key to one of the biggest puzzles in cosmology: why the universe is expanding faster than expected. Some theories suggest dark energy, the force behind this acceleration, interacts differently along these filaments, pushing voids apart while leaving dense clusters relatively untouched. Others propose that the web's structure itself could be warping our measurements, creating illusions in the way we perceive cosmic distances. Imagine blowing up a balloon with a grid drawn on it. If some lines stretch more than others, the entire geometry changes. But the most tantalizing idea, that the cosmic web isn't just a passive scaffold but an active player in the universe's evolution. Simulations show that shockwaves from colliding filaments could heat intergalactic gas to millions of degrees, sparking bursts of star formation or even feeding supermassive black holes. There's also the eerie alignment of galaxy spins. Many seem to rotate in sync with nearby filaments, as if the universe itself is orchestrating a silent, grand ballet. What's humbling is how much we still don't see. Upcoming telescopes like the European Space Agency's Euclid mission aim to map the cosmic web in 3D, teasing out the subtle ways dark matter and dark energy sculpt the universe. Every new thread we uncover could rewrite our understanding of gravity, expansion, and even the fate of the cosmos, because the cosmic web isn't just a backdrop, it's the loom on which reality is woven, and we're only just beginning to trace its pattern. On August 17, 2017, the universe handed scientists a treasure chest, and it was literally filled with gold. For the first time, gravitational wave detectors LIGO and Virgo caught ripples in spacetime from a cataclysmic event 130 million light-years away, two neutron stars spiraling into each other in a violent cosmic dance. But the real magic happened when telescopes around the world swiveled to watch the aftermath. What they saw wasn't just a flash in the dark, it was the birth certificate of precious metals. For decades, astronomers had theorized that the universe's gold, platinum, and uranium were forged in the extreme conditions of neutron star collisions. This event, catalogued as GW170817, was the smoking gun. Picture the scene: two city-sized stellar corpses, each more massive than the Sun, but compressed into a sphere just 12 miles wide, locked in a death spiral. As they collided at a third the speed of light, their cores merged into a fleeting superdense object, spewing jets of radioactive debris into space. This wasn't just any debris, it was a soup of neutrons so dense that atoms couldn't hold together. In the chaos, protons and neutrons slammed together, building heavier and heavier elements through a process called rapid neutron capture, or the R process. Within seconds, mountains of gold and platinum crystallized from the inferno, later scattered across the cosmos like cosmic confetti. The numbers are staggering. Simulations suggest a single neutron star merger can produce up to 10 times Earth's mass in gold alone. That means the jewelry on your finger, the circuitry in your phone, they might all contain atoms born in explosions older than dinosaurs. But the implications go beyond bling. This event confirmed that half the periodic table's heaviest elements, including uranium and iodine essential for life, are likely forged in these collisions. It's alchemy on a galactic scale, with neutron stars as the universe's ultimate crucibles. Now imagine the future, with upgrades to gravitational wave detectors like LIGO and next-generation telescopes like the Vera Rubin Observatory coming online. We're on the brink of catching these cosmic gold factories in the act regularly. Each new detection could reveal variations. Some collisions might produce more platinum, others rare earth metals. There's even speculation that certain neutron star mergers could forge exotic super-heavy elements unknown on Earth, hinting at a richer, more diverse periodic table than we've ever imagined. What's thrilling isn't just the confirmation of an old theory, but the door it opens. Neutron star collisions aren't just making gold. They're rewriting the story of how the universe seeds itself with the building blocks of planets, life, and even technology. Every time you hold a piece of jewelry, you're holding stardust, but some of it might be the ashes of a cosmic collision older than humanity itself. And with every new merger we detect, we're piecing together the recipe for how the universe turns death into creation. The Sun's surface roasts at a blistering 5,500 degrees Celsius, hot enough to vaporize diamonds. But venture just a few thousand kilometers above, into the wispy outer atmosphere called the corona, and temperatures skyrocket to over 1,000,000 degrees. It's as if you stepped away from a campfire and suddenly found yourself inside a blast furnace. This cosmic contradiction, known as the coronal heating problem, has baffled scientists for decades. How does the Sun's atmosphere grow hundreds of times hotter than the visible surface below? The answer might rewrite our understanding of stars, and it's hiding in the chaotic dance of magnetic fields and explosive energy bursts we're only beginning to decode. One leading theory points to nanoflares, tiny, relentless explosions peppering the Sun's atmosphere. Unlike the massive solar flares that light up headlines, these are minuscule, each packing just a billionth of a flare's energy. But what they lack in size, they make up in sheer numbers. Imagine popping popcorn. A single kernel won't heat a room, but a constant barrage might. Nanoflares could work the same way, collectively turning the corona into a simmering pressure cooker. The Parker Solar Probe, humanity's first mission to touch the Sun, has flown closer than any spacecraft before, skimming just 7 million kilometers from the solar surface. Its instruments have detected countless tiny energy bursts, fueling hopes that nanoflares are indeed the corona's hidden furnaces. Then there's magnetic reconnection, a process so powerful it can twist space itself. The Sun's magnetic field lines are constantly tangling and snapping like overstretched rubber bands. When they break, they release staggering amounts of energy. Think of the crack of a whip, but scaled up to cosmic proportions. This energy doesn't just vanish, it heats the surrounding plasma to unimaginable temperatures. The European Space Agency's solar orbiter recently captured stunning footage of these magnetic loops writhing like serpents, their collisions sparking waves of heat that ripple through the corona. But the mystery deepens. Why doesn't this heat dissipate? On Earth, heat rises and escapes, but the corona somehow traps it, creating a sustained inferno. Some scientists suspect plasma waves, vibrating at frequencies too high for our current instruments to fully detect, might act like invisible conductors, shuttling energy through the solar atmosphere. Others wonder if turbulence, the same chaotic force that rattles airplanes, could be stirring the corona into a perpetual heat engine. The stakes are higher than stellar physics. Unlocking the corona's secrets could revolutionize space weather forecasting, helping us predict solar storms that threaten satellites and power grids. Every time the Parker probe dives closer, braving temperatures that would melt steel, it sends back data that chips away at the mystery. And with each answer, we're not just solving a puzzle, we're learning how stars across the universe turn magnetism and chaos into light and heat. The sun's corona isn't just a scientific enigma, it's a masterclass in the invisible forces that shape our cosmic neighborhood. Venus has always been Earth's twisted sister, a hellscape of crushing pressures, scorching temperatures, and skies choked with sulfuric acid. But in 2020, astronomers dropped a bombshell that made us rethink everything. Traces of phosphine, a toxic gas that shouldn't survive in Venus' corrosive clouds, were detected in concentrations that defied all known chemistry. On Earth, phosphine is almost exclusively produced by microbes thriving in oxygen-free environments like swamps or the guts of penguins. Could this be the first whiff of alien life, floating in the temperate layers of Venus' upper atmosphere? Or is there a stranger, more exotic explanation hidden in the planet's fiery geology? The discovery sent shockwaves through the scientific community. Using the ALMA and James Clerk Maxwell telescopes, researchers spotted phosphine's spectral fingerprint at parts per billion levels, a signal too strong to dismiss as noise. The real puzzle: Venus' environment should obliterate phosphine within minutes. Sunlight and sulfuric acid would tear the molecules apart unless something, or someone, was continuously replenishing them. That's where the biological hypothesis ignites. Some extremophile microbes on Earth thrive in similarly hostile conditions, like the acidic hot springs of Yellowstone or the depths of volcanic vents. Could Venus clouds, with their balmy 30°C zones, harbor floating microbial colonies? It's a wild idea, but not impossible. Life as we know it is relentlessly adaptable. Yet skeptics countered with a volcanic lifeline. Venus is riddled with ancient volcanoes, and some studies suggest phosphine could form in magma-rich environments under extreme pressures. But here's the catch: we've never observed active volcanism on Venus producing phosphine, and the amounts detected would require eruptions of unimaginable scale. Recent simulations show that even if Venus were volcanically hyperactive, it's unlikely to generate the observed phosphine levels without invoking unknown chemistry. That leaves us with two equally thrilling possibilities. Either we're missing a fundamental piece of Venus' geologic puzzle, or we're staring at the first credible hint of life beyond Earth. The stakes couldn't be higher. If phosphine is biotic, it rewrites the rules of where life can exist. A planet with surface temperatures hot enough to melt lead and atmospheric pressures that crush submarines would suddenly become a beacon for astrobiologists. Future missions like NASA Da Vinci and Veritas or Europe's Envision aim to probe Venus' atmosphere and geology with unprecedented precision. Imagine a probe parachuting through those acidic clouds, scanning for complex molecules or even microbial structures. The phosphine mystery isn't just about one gas, it's about whether life is a cosmic fluke or a universal inevitability. For now, Venus keeps its secrets. But every time we look closer, the universe reminds us, life, if it's out there, won't conform to our expectations. It might lurk in the unlikeliest corners, thriving in conditions we once thought unsurvivable. And whether the answer is volcanoes or microbes, the phosphine puzzle is a wake-up call, a sign that even our nearest planetary neighbor still has stories left to tell. Mars holds its breath, or does it? Since landing in 2012, NASA Curiosity rover has sniffed out something baffling in the thin Martian air: sporadic bursts of methane, a gas that on Earth is overwhelmingly tied to life. These detections aren't constant, they spike unpredictably, sometimes vanishing within hours, leaving scientists scrambling to explain their origin. The puzzle lies in methane's fragility. Sunlight and chemical reactions should break it down within a few hundred years, so these whiffs suggest something on Mars is actively replenishing it. But what? The answer could rewrite our understanding of the red planet, revealing anything from hidden geothermal activity to, just maybe, the first whispers of extraterrestrial biology. The geological explanations are intriguing but fraught with holes. Methane can seep from underground when water reacts with certain rocks, like olivine, in a process called serpentinization. Mars has plenty of these minerals, and if pockets of liquid water still lurk deep below the surface, they could theoretically feed this reaction. Yet Curiosity's data reveals a hitch. The methane spikes don't correlate with seasonal changes or temperature shifts, as you'd expect if geology were the sole culprit. Even stranger, Europe's Trace gas orbiter, circling Mars, has mostly failed to confirm the rover's findings from orbit. This discrepancy could mean the methane is highly localized, perhaps seeping from tiny cracks near Curiosity's path before dispersing too quickly for satellites to catch. Then there's the electrifying alternative, microbes. On Earth, microorganisms called methanogens thrive in oxygen-free environments like swamps and animal guts, belching methane as a byproduct. If similar organisms exist beneath Mars' barren surface, shielded from radiation in briny aquifers, they could produce these fleeting gas plumes. The idea isn't far-fetched. Methanogens are ancient, hardy, and could have hitchhiked on meteorites between planets during the solar system's chaotic youth. But proving it, that's the rub. Without catching a microbe red-handed, scientists rely on isotopic fingerprints. Life-created methane tends to favor lighter carbon isotopes, while geologic processes don't discriminate. So far, Curiosity's limited instruments haven't settled the debate, leaving the door cracked for both possibilities. Future missions could slam that door shut or kick it wide open. NASA Perseverance rover, armed with sharper tools, is scouring Jezero crater for organics but lacks a dedicated methane sniffer, the real game changer. Sample return missions. If Martian soil fetched to Earth contains microbes or their fossilized remains, the case for life would skyrocket. Meanwhile, Japan's Amuamua mission to Phobos might inadvertently settle the debate. If traces of Martian methane cling to the Moon's surface, ejected by ancient impacts, it could hint at a planet-wide phenomenon. For now, Mars keeps its secrets close. Each methane spike is a tantalizing breadcrumb, leading us toward answers that could range from mundane to revolutionary. Whether the source is a subterranean chemical factory or the faint breath of Martian microbes, one thing's certain: the red planet is far from dead. It's dynamic, cryptic, and waiting to reveal whether we share the cosmos with neighbors or if we're truly alone. In April 2019, astronomers monitoring the Parkes radio telescope in Australia detected something that sent a jolt through the scientific community: a narrow-band radio signal clocking in at 982 MHz, emanating from Proxima Centauri, the closest star system to our own. Dubbed BLC-1, this signal wasn't just any cosmic static. It was laser-focused in frequency, drifting in a way that mimicked the movement of a planet, and most intriguingly, it appeared only when the telescope was pointed at Proxima Centauri. For a heart-stopping moment, it seemed like we might have stumbled upon a deliberate transmission from our interstellar neighbors. The signal's characteristics were uncanny. Unlike the usual broadband noise from stellar flares or pulsars, BLC-1 was confined to a razor-thin slice of the radio spectrum, the kind of precision you'd expect from engineered technology, not natural astrophysics. Even more compelling, Proxima Centauri hosts at least 2 planets, including Proxima b, a rocky world nestled in the star's habitable zone. Could this be a beacon from a civilization reaching out across the 4.2 light-year void? The idea wasn't just thrilling, it was plausible enough to warrant a full-scale investigation by Breakthrough Listen, a project dedicated to scanning the skies for extraterrestrial intelligence. But the universe rarely serves up easy answers. As researchers dug deeper, cracks began to appear in the alien hypothesis. The signal's drift rate, initially thought to align with planetary motion, turned out to be inconsistent. Then there was the absence of repetition despite months of follow-up observations. BLC-1 never reappeared. Most damningly, further analysis revealed the signal's frequency overlapped with known human-made interference, likely a stray transmission from a passing satellite or ground-based equipment. By 2021, the consensus tilted heavily toward a terrestrial origin, though the exact source was never pinned down. Yet the Proxima signal's legacy lingers, not as a false alarm, but as a dress rehearsal for the real thing. It highlighted the immense challenges of distinguishing artificial signals from natural noise in an era cluttered with radio pollution. Future detections will need to pass stricter tests, verification from multiple telescopes, polarization analysis, and ideally, a repeating pattern that rules out human error. Projects like the upcoming Square Kilometre Array, with its unparalleled sensitivity, could be game changers, filtering out earthly interference while scanning millions of frequencies simultaneously. What makes BLC-1 so fascinating isn't just the what-if of alien contact, but the meticulous detective work it inspired. It reminded us that the line between discovery and illusion is razor-thin, and that every anomalous blip demands both open-mindedness and ruthless skepticism. Proxima Centauri hasn't given up its secrets yet, but the next time a signal like this appears, we'll be ready to listen harder, question deeper, and maybe, just maybe, hear a whisper from the stars that changes everything. Long after sunset, when the last glow of twilight fades, a faint triangular radiance sometimes rises from the horizon, a celestial pyramid of soft light stretching upward through the constellations. This ghostly glow, known as the Zodiacal light, has puzzled skywatchers for centuries. At its core lies a simple cosmic mystery. What fills the inner solar system with so much dust that it scatters sunlight into this ethereal display? The answer isn't just about beauty, it's a window into the violent construction zone our planetary system once was, and the unseen debris still swirling around us today. For decades, astronomers assumed comets were the primary culprits. As these icy wanderers swing close to the sun, they shed layers of dust like cosmic breadcrumbs, leaving trails that Earth plows through during meteor showers. The logic seemed sound until spacecraft like Rosetta studied comet dust up close and found its composition didn't quite match the zodiacal light's spectral fingerprint. Cometary particles tend to be fluffier, richer in organic compounds, while the zodiacal dust appears denser and more mineral-rich. That discrepancy sent scientists scrambling for alternatives, and asteroids emerged as surprising contenders. Main belt asteroids grind against each other over eons, producing fine debris that spirals inward toward the Sun. Japan's Hayabusa missions confirmed asteroid dust shares striking similarities with the Zodiacal cloud, particularly in its crystalline structure. But here's where the plot thickens. Recent observations reveal the Zodiacal dust belt isn't uniform. It contains strange clumps and asymmetries that suggest a more dynamic origin story. One leading theory points to dust avalanches, where collisions in the asteroid belt create temporary surges of particles that spiral sunward in waves. NASA Juno spacecraft even spotted an unexpected dust ring near Mars, possibly fed by the red planet's moons Phobos and Deimos, adding another piece to the puzzle. Some researchers now suspect a hybrid origin. Asteroid collisions provide the bulk of the material, while occasional comet visitors contribute volatile, rich grains, creating a diverse interplanetary dust cocktail. The most fascinating twist connects this dust to Earth's own origins. These particles aren't just debris, they're time capsules from the solar system's construction phase. When planets formed 4.5 billion years ago, countless smaller bodies shattered in the process, filling the young system with primordial dust. The zodiacal light we see today might be the last whispers of that ancient chaos, a fading echo of the violence that built our cosmic neighborhood. Missions like LISA, the upcoming space-based gravitational wave detector, could soon trace how this dust influences the orbits of planets over time, revealing how even the tiniest particles shape grand celestial mechanics. What makes this mystery so compelling isn't just the science, it's the way this delicate glow bridges past and present. Every photon of zodiacal light carries a story, from the asteroid collisions of today back to the dusty dawn of our solar system. And when you stand under a moonless sky, watching that pale pyramid climb through the stars, you're not just seeing scattered sunlight, you're witnessing the afterglow of creation itself. Every story has an ending, but the universe's final chapter is anything but certain. Will it collapse inward in a fiery crescendo, fade into eternal stillness, or reboot in an endless cycle of cosmic rebirth? The answer hinges on a tug-of-war between forces we've only begun to understand, and each possible outcome is more mind-bending than the last. Take the Big Crunch, a dramatic finale where the universe reverses its expansion. Picture this: dark energy, the mysterious force currently accelerating galaxies apart, weakens over time, allowing gravity to regain control. Galaxies would start rushing toward each other, their light blue shifting as space itself contracts. Temperatures would soar until stars, planets, and even atoms are ripped apart in a singularity hotter than the Big Bang itself. It's cosmic poetry, a universe born from fire returning to fire. But here's the catch. Recent measurements of dark energy suggest it's not weakening. If anything, it's holding steady or growing stronger. Unless something drastic changes, the crunch seems unlikely. That brings us to heat death, the universe's slow sigh into darkness. In this scenario, dark energy keeps stretching spacetime until galaxies vanish over each other's horizons, their light stretched beyond detection. Stars burn out, black holes evaporate via Hawking radiation, and all energy disperses into a lifeless, lukewarm haze. Entropy, the universe's tendency toward disorder, reaches its peak, leaving no Chinese letter, no structure, just a vast, featureless void where time loses meaning. It's a chilling thought, but not inevitable. Some theorists argue quantum fluctuations could spark new big bangs in the emptiness, like bubbles forming in an infinite cosmic foam. Which leads to the most tantalizing idea of all, a cyclic universe. Imagine our cosmos as one page in an infinite book, each chapter ending in a big crunch that births the next big bang. String theory hints at this possibility, with colliding branes, higher dimensional membranes triggering rebirths. Even the CMB's so-called axis of evil, anomalies in the cosmic microwave background, might be scars from a pre-Big Bang universe. The math is speculative, but the allure is undeniable. An eternal rhythm of creation and destruction, where every ending is a new beginning. What's breathtaking isn't just the scale of these scenarios, but how they reframe our place in the cosmos. Whether the universe collapses, freezes, or reboots, we're witnesses to a fleeting moment in its epic timeline, a spark of consciousness in the darkness, daring to ask what comes next. And that's the ultimate mystery, not just how the story ends, but whether endings are even real or just turns in an infinite cosmic spiral. What if our universe isn't the only one? Imagine a cosmic tapestry so vast it contains countless other universes, each with its own laws of physics, its own versions of stars and planets, even alternate versions of you. This isn't science fiction. It's the multiverse hypothesis, a radical idea growing from the bedrock of quantum mechanics and string theory. And while it sounds fantastical, some of the brightest minds in physics argue it might be the only way to explain the peculiar fine-tuning of our own universe. Let's start with the simplest version, the Level 1 multiverse. Picture space stretching infinitely beyond the observable horizon. Given enough room, particles can only arrange themselves in so many ways. Eventually, patterns must repeat. Somewhere out there, an identical Earth might exist, where every choice you didn't make here played out differently. This isn't magic, it's statistics. If the cosmos is truly infinite, then every possible configuration of matter becomes inevitable. The catch: we'll never see these parallel worlds. They lie beyond a horizon set by the speed of light, forever out of reach. Then things get weirder. Enter the Level 2 multiverse, where entire bubble universes sprout from an eternally inflating cosmos. According to string theory, the vacuum of space isn't empty. It's a seething quantum foam where tiny fluctuations can trigger new big bangs. Each bubble universe might have different physical constants, a place where gravity is stronger, light slower, or where atoms never formed at all. This isn't just speculation, it's a natural extension of cosmic inflation, the theory that our universe underwent exponential expansion in its first moments. If inflation happened once, why couldn't it happen endlessly, birthing a fractal of universes? The real puzzle is proof. How do you test something fundamentally disconnected from our reality? Some theorists hunt for cosmic bruises, anomalies in the cosmic microwave background where our universe might have collided with another. Others suggest subtle gravitational imprints from neighboring universes warping spacetime. So far, no smoking gun, but absence of evidence isn't evidence of absence. The multiverse might simply exist on scales or dimensions we're not equipped to measure. Here's the beautiful irony. The multiverse could solve one of physics' biggest riddles: why our universe seems perfectly tuned for life. If countless universes exist with random laws, of course we'd find ourselves in one where conditions allow galaxies, planets, and thinkers. It's the ultimate selection bias, but that also makes the multiverse frustrating. If every possible outcome exists somewhere, does science lose its predictive power? Or does it simply mean reality is grander and stranger than we ever dreamed? The debate rages on, with heavyweights like Stephen Hawking and Roger Penrose on opposing sides. For now, the multiverse remains a dazzling possibility, a reminder that the universe's greatest mysteries might not lie in the stars, but in the voids between them, where other worlds, other stories, other versions of everything might quietly unfold, unseen but undeniable. Every mystery we've explored, dark matter's ghostly grip, black holes devouring information, even the faintest whispers of alien signals, isn't just a puzzle to solve. These are cosmic invitations calling us to question, to imagine, and sometimes to tear up the textbooks and start fresh. Science isn't a static set of facts, it's a living conversation, a back and forth between what we think we know and what the universe reveals when we dare to look deeper. And that's the thrill, not just the answers, but the questions that unravel them. Consider how far we've come. A century ago, galaxies beyond our own were debated as mere spiral nebulae. Now we map the cosmic web's filaments, hunt for planets made of diamond, and ponder realities beyond our own. Yet with every discovery, the universe expands not just outward, but inward, revealing layers of complexity we never anticipated. Dark energy's relentless push, the Great Attractor's invisible pull, even the hexagonal storms on Saturn, they all whisper the same truth. Reality is far stranger, far more inventive than our boldest theories. This isn't just about astronomy, it's about how we fit into the story. Every anomaly, every contradiction, is a reminder that curiosity is our superpower. When Voyager's engineers puzzled over the Pioneer anomaly, they didn't dismiss a few millimeters per second. They chased them, uncovering thermal whispers in the dark. When Tabby's star flickered, thousands of volunteers joined the hunt, proving science isn't just for labs and universities. It's for anyone who's ever looked up and wondered. Carl Sagan once said, "Somewhere, something incredible is waiting to be known." That's the heartbeat of exploration. Whether it's a hidden planet tugging at the Kuiper belt or a radio burst defying physics, the cosmos keeps its most dazzling secrets just beyond our reach, not to taunt us, but to keep us reaching. So stay curious, support the telescopes scanning the skies, the probes braving alien atmospheres, the theorists scribbling equations at midnight, because the next great revelation, it's out there, and with every question we ask, we're one step closer to turning the unknown into the unforgettable.